Hello everyone and welcome. This is General Chemistry 2 or Chem 152, lecture number 14. This is the first lecture of Unit 3 in my course, and it's the first of several lectures on acids and bases. This one, we're going to learn about the definitions of acids and bases. We're going to learn about what conjugate acids and bases are, and then remind ourselves on what strong versus weak means, and analyze the way we can break down acid strength. This covers OpenStax sections 14.1 through 14.3. So first, what are acids and bases? Acids and bases are two general classes of chemicals that we can characterize based on their physical and chemical properties. They are not isolated to a lab. We see them everywhere in everyday life. So oftentimes, many different cleaners you use in real life, like some of this drain cleaning gel, oven cleaner, baking soda, milk of magnesia. These are all examples of bases. Acids are often sour, so usually like soda will usually have some type of acid in it. If you look at the nutrition facts on a soda, cucumbers, especially citrus fruits, coffees, are all slightly acidic. Things that have a little bit of a bite to them or maybe are a little sour tend to be acidic. So vinegars, lemons, and importantly, humic stomach acid or stomach fluid contains some commonly encountered acids. Acids will corrode some minerals and metals. Acids will typically donate or give off H plus ions, also known as protons, and we'll explain this a little bit more later. Chemical formulas for acids almost always start with an H. The only exceptions you may see is oftentimes organic acids, which are sometimes referred to as carboxylic acids, may list the H last in the formula as part of a larger COOH group. So this here is the molecular structure of acetic acid. So we have two carbons. This carbon is single bonded to three hydrogens. This one double bonded to an oxygen, single bonded to this oxygen, which is then single bonded to a hydrogen. And so this hydrogen right here is what we refer to as the acidic hydrogen or the acidic proton that is lost when this acid donates a hydrogen or donates a proton. So you may see acetic acid written as HC2H3O2. This is the common way of writing acids with that acidic hydrogen out front, but this is what's referred to as an organic or carboxylic acid. So this is called a carboxyl group. And so you may see the COOH, which refers to these four atoms right here. You may see that written at the end of the formula, but the vast majority of the time, acids are written with the hydrogen out front. Bases are commonly found in products such as Drano, oven cleaners, Windex, which contains ammonia, and antacids. They often feel slippery to the touch. This is because they cause a chemical reaction which turns the top oily layer of your skin into a soap-like substance. Many bases contain the hydroxide ion. So in fact, most bases contain the hydroxide ion. Most of the ones that we're going to look at. So hydroxide, as a reminder, is OH minus. So NaOH, sodium hydroxide. MgOH2 is magnesium hydroxide. Another very common base is ammonia, or NH3, shown here. This is an example of a weak base, which we will learn about a little more later. Make sure you don't confuse this with the ammonium ion, which is one of the polyatomic ions you learn about in Gen Chem 1, which is NH4+. All right, a little bit of quick review on naming acids and bases. Many bases contain hydroxides, and these are named using the rules for naming ionic compounds. So NaOH is sodium hydroxide, CaOH2 is calcium hydroxide. The major exception that you'll see is NH3, which is referred to as ammonia. This is technically the common name. You will just use the common name here, but you could name this using the covalent compounds rule and call this nitrogen trihydride, but you're going to see it referred to just by its common name, ammonia. To name acids, we need to determine which type of acid we're dealing with. We're either dealing with a binary acid, which is hydrogen and just one other type of element, so HCl or H2S are two examples, or you're dealing with an oxyacid. Oxyacids is when you have a hydrogen and a polyatomic ion which contains oxygen, so an hydrogen and an oxyanion, like HNO3, H2SO4, H3PO4, and so on. Binary acids, again, have that formula with the pattern HNX. H followed by a single other element. To name a binary acid, we use the prefix hydro instead of the word hydrogen. So we replace the ending of the other element X with IC acid. So for example, to name HCl, we use the prefix hydro instead of the word hydrogen. The other element Cl is chlorine. This becomes chloric acid, and then you put those two words together and you get hydrochloric acid. So the name of HCl is hydrochloric acid. And this convention will go for all binary acids. The only major exception is cyanide. Cyanide is a polyatomic anion with the formula Cn-. Cyanide is actually also named like a binary acid despite having two types of elements. So the acid HCN would be hydrocyanic acid. What about the name of HBr, or what about H2S? I'd encourage you to pause the video and see if you can come up with the names of these two acids. All right, first one, HBr, would be hydrobromic acid, and the second one, H2S, would be hydrosulfuric acid. Okay, a brief review on naming oxyacids. Oxyacids are acids that contain an oxyanion. So they contain oxygen, which is part of a polyatomic ion. These oxyacids are named based on the polyatomic ion they contain. So polyatomic ions that end with 8 become IC. Polyatomic anions that end with ITE become OUS. So for example, HNO3 contains nitrate, so NO3 is nitrate. The 8 ending becomes IC acid, and so we get simply nitric acid. Leave off the hydro prefix, that's only for binary acids. If we had the acid HNO2, you would recognize that NO2 is nitrite, and then the ite becomes OUS, so HNO2 would be nitrous acid. There are a couple acids that don't follow these rules quite exactly. So a good example of this is H2SO4. SO4 is sulfate, but this acid, H2SO4, is actually sulfuric acid. This most commonly comes up with the sulfur and phosphor compounds, where a UR or an OR is added back in, I think just for nomenclature reasons, just because the pronunciation sounds better. If you follow these rules exactly, sulfate would become sulfic acid, but it's actually sulfuric acid, or you'll see this on the next slide here with this compound as well. PO4 is phosphate, so technically this should be phosphic acid, but an OR is added back in, so it's phosphoric acid. So here are several different examples for how we can name binary acids and oxyacids. So if you feel like you need more practice with these, please go ahead and pause the video and maybe try going back and forth between the names and the formula for additional practice. All right, now onto the definitions of acids and bases. Different scientists through the years have defined the terms acids and bases in different ways. In this class, we're primarily going to focus on the most commonly used definition, which is known as the Bronsted-Lowry definition. In the Bronsted-Lowry definition, we define an acid as a species that donates or gives off an H+ ion or proton. Bases then accept or take up H+ ions. The definition you may have learned about in Gen Chem 1 was the Arrhenius definition. The Arrhenius definition is the most specific definition in which acids increase the amount of H+ in solution and bases increase the amount of OH- in solution. The Bronsted-Lowry definition is a little more general, and it's the most commonly used definition. It's the one we're going to use here. If you move on to organic chemistry, you're going to learn about Lewis acids and bases, which are even more general than the Bronsted-Lowry definition and rely on a definition of the movement of electrons instead of H+ ions. But again, key here to know in this course, acids donate or give off H+ ions, bases accept H+ ions. That's what you need to know for acids and bases here. So when acids are in aqueous solution, what will generally occur is the H2O, the water, will combine with the H+ given off by the acid, forming a hydronium ion. And hydronium is the polyatomic ion H3O+. It's essentially the protonated form of water. It's water plus an H+ ion. So HCl plus H2O would form H3O+. plus Cl minus. So the H plus from the hydrochloric acid is donated to water, and water then becomes the hydronium ion, and then see what's left behind is the Cl minus. Or if we had hydrofluoric acid, HF plus H2O forms H3O plus and F minus. When bases are in aqueous solution, they either release hydroxide directly into solution, or the base takes H plus away from the water, which forms hydroxide ions. So most of the bases we're going to see, most of the strong bases, so the bases with hydroxide in the formula, what occurs here is they don't actually need to interact with water. They will simply, once they are dissolved in water, they will split apart. So it's like an ionic compound that just splits apart into its ions. So sodium hydroxide simply splits in half and forms the Na plus ions, and importantly for us, the OH minus ions. So these hydroxide ions here are what's indicative that we have a base present. If you have like a weak base like NH3, the NH3 doesn't directly release hydroxide. Rather, the NH3 will react with water. It will accept an H plus from the water, and we get NH4 plus. So this is NH3 accepts NH plus and forms NH4 plus. And then importantly, what's left from the water is OH minus. A brief note here on notation. You've noticed that I've used the phrase both H plus and proton. We can use these terms interchangeably. So we can say H plus, we can say proton, or we can also say H3O plus. So H plus ions, protons, or hydronium ions. We can use all of these interchangeably to represent the product of acid dissociation, or essentially what makes an acid an acid. In aqueous solutions, H plus associates with H2O to form H3O plus. They are considered roughly the same thing in the aqueous phase. So you could write the dissociation like this, where you show HF breaking into H plus and F minus, and this is you may have seen it written this way in Gen Chem 1 to keep things simple, but we're primarily going to write it like this. We're going to show the dissociation reaction with water, so HF plus H2O forming H3O plus and F minus, and this is what's indicative of the acid dissociation, the H3O plus that forms. All right, so most of the acids we're going to analyze, they release only one proton into solution. These are known as monoprotic acids, so like nitric acid or hydrofluoric acid or hydrochloric acid. Most of the examples we will see are referred to as monoprotic, meaning they release just one proton into solution. There are some acids which have 2 or even 3 hydrogen ions that can be released into solution. These are known as diprotic for 2 or triprotic for 3. So some good examples of this would be sulfuric acid. Sulfuric acid is technically a diprotic acid because it has 2 acidic hydrogens. So one hydrogen is released and we get H plus HSO4. We still have another acidic hydrogen that can be released, and so we get a second H plus forming and just leaving the sulfate ion behind. Or phosphoric acid. Phosphoric acid is a good example of a triprotic acid. Oh, sorry about that. I just had to pause the recording there briefly. So that's why the slides suddenly jumped backwards. Okay, next, on to conjugate acid-base pairs. So here, looking at the acid-base reaction between ammonia and water, so NH3 plus H2O forming NH4 plus and OH minus. Here we're going to learn about conjugate acids and bases. So we're going to pose a question: what do the curved arrows here indicate? What is happening here? Or more importantly, how are these arrows related to each other? We'll be able to answer these questions after the information on the following couple of slides. So an acid-base reaction can be thought of as a paired reaction. The acid is losing a proton and the base is gaining a proton. So in this reaction here, we should notice that NH3 is the base. Notice that NH3 is gaining a proton and it goes from being NH3 to NH4 plus, whereas water is acting as the acid. On the left side, it's H2O, and on the right side, it's OH minus. So from the left to the right, water is losing a proton, or we could say that it's donating a proton. So this makes water the acid. So you could split this into half reactions, where you could say H2O gives off an H plus OH minus, and then NH3 accepts an H plus to form NH4 plus, and then recombining those two half reactions would give you that overall acid-base reaction we saw on the previous slide. So here, again, water is the acid, ammonia is the base. Now to analyze what conjugate means here, we're going to think of an acid-base reaction in the same way that we think of a ball being tossed between a pitcher and a catcher. And I know this analogy is a little silly, but hopefully it makes this idea make sense. So we're going to think of the ball here as being the proton, the H plus that's being thrown back and forth. So in this analogy, we can think of the acid like the pitcher, right? The acid is the one donating the H plus. So we could say that the acid is the pitcher who is throwing the ball, is throwing the H plus. The base is therefore like the catcher. It's receiving the ball. It's accepting the H plus. So water, the acid, is going to be throwing the H plus, throwing the ball to the catcher. The base, NH3 plus. Now, once we are on the product side, after the pitcher has thrown the ball, they don't have the ball anymore, so they can't throw the ball, but they could now catch the ball, right? After the pitcher throws the ball, now the catcher has the ball in his or her hand. So after the catcher has caught the ball, they have the ball now, so they can't catch it anymore, but they could now throw the ball, right? So what we can say here then is their roles have reversed. Their roles have reversed, and so let's look at things from the product side. Once that H plus has been passed from the pitcher acid to the catcher base, we can now look at the situation on the product side of the reaction. What used to be the catcher, the base, now has the ball, or now has the H plus, so it can now act as the pitcher. And what used to be the pitcher, the acid, now has an empty glove, no ball, so it can now act as the catcher. So basically, if we're running this reaction in the reverse direction, or in this baseball analogy, the catcher is now going to throw the ball, or throw the H plus, back to the pitcher, who's now basically acting as the catcher. So we give these products special names. Because the former catcher, the base, now has the ball, it can now act as the pitcher, and it is called the conjugate acid. So because this former base, right, the former base now has the ball, it has the H plus, it's going to act as the pitcher in the reverse direction. It is called the conjugate acid. Then similarly, because the former pitcher, or the former acid, now doesn't have the ball, it can now act as the catcher, or the base, and it is referred to as the conjugate base. So I hope this analogy made some sense. I hope this wasn't a little too contrived. All of this to say, when an acid has lost a proton, a conjugate base is formed. When a base has gained a proton, a conjugate acid is formed. So here, to label this, we refer to as NH3. NH3 is the base, which makes its partner, NH4 plus, the conjugate acid. H2O was the acid, and its partner, OH minus, is now referred to as the conjugate base. And that is summarized here on this slide. Acid, after throwing the H plus, it becomes the conjugate base. Base, after catching the H plus, it becomes the conjugate acid. Okay, and that analogy is summarized further here. All right, let's do a little practice with conjugate acid-base pairs. I would like you to pause the video and label each chemical species in this reaction as either the acid, the base, the conjugate acid, or the conjugate base. Okay, I also have a couple hints down below here. And I have 2 more practice problems right here. The answers to all 3 practice problems, the one on the previous slide, plus these 2, will be on the next slide. So please, again, go ahead and pause the video and try these 2 practice problems. Label each chemical species in the reaction as either the acid, base, conjugate acid, or conjugate base. All right, and here are the answers to each of these problems. All right, one more practice problem for you to try. Please pause the video, and given the bases below, what are the conjugate acids of each? All right, so we should know that the conjugate acid is what's formed after the base gains an H+. So all you need to do here is to add an extra hydrogen to each formula and then increase its charge by +1. So if we have the base NH3, the conjugate acid would be NH4+. If we have a base F-, the conjugate acid would be HF. If we have the base H2O, the conjugate acid would be H3O+. And if we have the base CH3 2-, the conjugate acid would be HCO3 -1. Another problem for you to try. Please pause the video, and given the acids below, what are the conjugate bases of each? All right, so the conjugate base is what's formed after the acid loses an H+. So here you should be doing the reverse of the previous problem, remove a hydrogen from each and decrease its charge by 1. So if we have the acid HBr, the conjugate base would be Br-. H3PO4 gives H2PO4-. H3O+ gives H2O, and HSO4- gives SO4 2-. All right, next we are going to look at neutralization reactions. A neutralization reaction takes place between an acid and a base to produce a salt, essentially an ionic compound, and water. The salt produced depends on the acid and the base involved in the reaction. So consider the reaction below. NaOH plus HCl, this forms NaCl and H2O, a very common neutralization reaction. You probably saw this reaction referenced in Gen Chem 1. So the base, sodium hydroxide, plus the acid, hydrochloric acid, forms the salt, sodium chloride, and water. So the metal cation from the base, in this case sodium, Na+, and the anion from the acid, in this case chloride, Cl-, these combine to form the salt, sodium chloride. And then the hydroxide, the OH- from the base, combines with the hydrogen ion, the H+ from the acid, to form water. Quick question, what salt would be produced in the neutralization reaction of potassium hydroxide with hydrobromic acid? All right, the correct answer here would be potassium bromide. The K+ and the Br- would combine to form a salt, and then the OH- and the H+ would form water. I have a couple more practice problems for you to try, so please pause the video and try to predict the products formed by each of the following acid-base neutralization reactions. All right, so the answers are given here. Again, you need to take the metal cation from the base, combine it with the anion from the acid to form the salt, which leaves the H+ and OH- to form water as the other product. So that first reaction would give the products lithium fluoride and water. The second one would give the products rubidium nitrate and water. And the third one would give the products calcium sulfate and 2 moles of water. Notice it's H2SO4 plus CaOH2. We have 2 H+ ions and 2 OH- ions, and so we get 2 moles of water here instead of just 1 as in the previous examples. But then we get calcium sulfate as our salt here. All right, next we're going to look at strong acids and bases. We are going to define an acid as a proton donor or an H plus donor, again, per the Bronsted-Lowry definition we touched on earlier. To give off an H plus, an acid must dissociate or break apart. The H plus has to break away with the anion that remains from the rest of the acid. Strong acids are acids that dissociate completely. They give off 100% of their H+. Note the forward-only arrow in the equation below. So HCl forms H+, and Cl-. The forward-only arrow indicates that this acid dissociates completely. It gives off 100% of its H+. Strong bases also dissociate completely, so NaOH would completely dissociate into Na+ and OH-. An acid dissociates when it gives off H+ and splits into its component ions, as shown in those previous examples. Some acids dissociate more readily than others, leading to classifications of strong acids, which could also be referred to as strong electrolytes, versus weak acids, which can be referred to as weak electrolytes. So another example would be the strong acid nitric acid, which dissociates completely and irreversibly. A good example of a weak acid is acetic acid. This acid is a weak acid, so note the double arrows here. So this is actually an equilibrium reaction, and we'll learn more about the equilibrium constants of acids in another lecture, but you may have noticed a couple acid-base reactions earlier in this lecture that had double arrows. The double arrow here means it is a weak acid which dissociates reversibly. So acetic acid dissociates reversibly. So we get HC2H3O2 forms H+ and C2H3O2-, but double arrows because it is a weak acid that dissociates reversibly. Less than 100% of the acid dissociates. Another good example is hydrofluoric acid. A weak acid such as HF not only gives away its proton, but can also take it back. So note the equilibrium arrow in the reaction below. HF dissociates reversibly to form H+ and F-, but because this reaction is reversible, this reaction could change direction and reverse course, meaning the F- could recombine with an H+ ion to reform some HF. Similarly, the weak base ammonia, NH3, can accept H+ reversibly, meaning it doesn't become 100% protonated. So NH3 plus H+ forms NH4+, but again, note the double arrows indicating this is a weak base with a reversible reaction. So to summarize, strong acids and strong bases versus weak acids, weak bases, the same definition will hold for both, but a strong acid is one that is extremely reactive. It dissociates 100% completely. It's irreversible, and we have a forward-only reaction arrow. A weak acid is one that is not very reactive. It dissociates partially, so less than 100%. It is reversible, and so we use a double arrow. There are 7 strong acids I expect you to know: HCl, HBr, HI, HNO3, H2SO4, HClO3, and HClO4. These are the 7 strong acids I expect you to know. Any acid not on this list is a weak acid. I do also want to note, if you're not in my class and you are in a different class but just watching these videos because you find them useful, some professors, some sources don't list chloric acid. You may have 6 strong acids in your course. My students, I expect you to know 7 strong acids. I do think that chloric acid should be classified as a strong acid, but not every source, not every professor will include chloric acid amongst the strong acids. But these are the 7 I expect you to know. And similarly, there are 8 strong bases I expect you to know, or I expect you to know. The most commonly used strong bases are group 1 and group 2 metal hydroxides, so lithium, sodium, potassium, rubidium, and cesium hydroxide, and then calcium, strontium, and barium hydroxide. If you've got a periodic table in front of you, you can see where these are on the periodic table. It kind of looks like a Tetris block if you trace out these 8 elements in the periodic table on the left side of the table there. But these are the 8 strong bases I expect you to know. Anything not listed here can be considered to be a weak base. So strong bases, like strong acids, dissociate completely in aqueous solutions, and we use forward-only arrows in their reactions. So here are a couple sample dissociation reactions of strong bases. All right, let's do a little practice. Consider 2 solutions. Solution A is a 0.25 molar solution of hydrofluoric acid. Solution B is a 0.25 molar solution of nitric acid. Which of these 2 solutions would you predict to be more acidic? So think about this answer on your own, and then pause the video, and I'll reveal the answer on the next slide. All right, so solution A is a weak acid which dissociates reversibly, whereas solution B is a strong acid which dissociates completely and irreversibly. Both solutions are the same concentration, 0.25 molar, but solution B is going to dissociate 100%, while solution A will not. This means that solution B will give off all of its H+, converting them all into H3O+ ions. More H3O+ is created by solution B, therefore solution B is more acidic than solution A. All right, last topic to talk about in this lecture is molecular structure and acid strength. Given a monoprotic acid, which will generally be written as either HA or HX, H for the acidic hydrogen, and then you will see either A or X used to denote whatever the anion is that's paired with that acidic hydrogen. First question is, do you think that acid strength increases or decreases with bond strength? So I would like you to pause the video and consider this question. All right, the correct answer here is that acid strength is going to decrease as bond strength increases. So the stronger this bond is, the weaker the acid is going to be, because it's harder for the H+ to be donated. And that's what makes an acid an acid. It's the ability for an H+ to be donated. So why does this trend occur? What makes an acid an acid? Again, it's that H+ being given off. So if you look at these 4 acids down below, these are 4 binary acids. These are the halogen acids, so HF, HCl, HBr, and HI. Notice that the bond energy is decreasing going down the table from HF to HCl to HBr to HI. So play one of these things is not like the other with the table below. Does this follow with the trend? So what I am prodding you to think about here is the fact that HCl, HBr, and HI, all 3 of these were on that list of strong acids. These 3, hydrochloric, hydrobromic, and hydroiodic, are all strong acids, whereas HF, hydrofluoric, is a weak acid. And notice that HF, hydrofluoric acid, has the highest bond energy. So the one with the biggest bond energy is the weakest acid. So the trends you need to understand here, first, going across a row or across a period, so going left to right across a row, electronegativity is the primary variable affecting acid strength. So let's say HF versus HO. Both have hydrogen. Fluorine is more electronegative than oxygen. So fluorine is more electronegative, which pulls electrons away from the hydrogen, meaning this will form H+ more easily. So HF is a stronger acid than H2O. So when you are comparing 2 binary acids in the same row, the acid with the more electronegative anion is going to be the stronger acid. So if I asked you to compare HF versus HO, they are in the same row, in the same period. Fluorine is further to the right. Fluorine is more electronegative. Thus, HF, hydrofluoric acid, is the stronger acid here because it's pulling the electrons away from hydrogen, which makes it easier for that H+ to be peeled away, to be donated, making it the stronger acid. If you are comparing 2 binary acids that are in the same group instead, so the same column, size is the predominant factor. So if I were to compare HF versus HI, Size here determines bond length, which affects the acid strength much more than electronegativity. A larger atomic radius leads to longer bonds. Longer bonds are weaker and therefore break more easily. So if I were to compare HF versus HI, these are two acids that are in the same group or the same column, fluorine number 9, iodine number 53. They have relatively the same electronegativities. Fluorine is definitely more electronegative, but there's more of a similarity here because they're in the same column. So the important trend here is size. Iodine is much further down the periodic table. Iodine is therefore a much bigger atom. Because iodine is much bigger, the HI bond is much longer than the HF bond. Because the bond is longer, this bond is weaker. It breaks more easily. The H plus is therefore donated more easily, which makes HI the stronger acid. So to summarize, if you are comparing two binary acids in the same row, the same period, the one with the anion further to the right, the one with the more electronegative anion, is the stronger acid. If you are comparing two binary acids in the same column, size is the important factor, and so the anion that's further down that column is going to be the stronger acid. So let's have you try these two practice problems. Which is the stronger acid in each pair? Please pause the video and see if you can answer these two questions. All right, in this first pair, we're comparing H3P versus H2S. These two anions are in the same period, the same row. Therefore, the one further to the right, the one that is more electronegative, is the stronger acid, and so the correct answer would be H2S. In our second pair, H2O versus H2S, now we're comparing two anions that are in the same group or the same column. Therefore, the one that is further down the periodic table, the one with the bigger anion, will be the stronger acid. And so we again get the answer of H2S. All right, we're going to finish today by talking about trends in strength with regards to oxyacids. So for a given central atom, acid strength increases as the number of oxygens increase. So for the same number, sorry about that, let me back up, that's a different trend. So for a given central atom, acid strength increases as the number of oxygen increases. So this trend applies when you are comparing two oxyacids that have the same central atom. So if I were to compare phosphoric acid, H3PO4, versus phosphorus acid, H3PO3. They both have 3 hydrogens. Importantly, they both have the same central atom. So the stronger acid is the one with more oxygens. If you've got more oxygens, you've got more electron density being pulled away, and this allows the hydrogen to be more easily donated. So H3PO4 is going to be the stronger acid than H3PO3. If you are comparing two oxyacids that have the same number of oxygens but different central atoms, the acid strength increases as the central atom electronegativity increases. So if I were to compare HClO3 versus H2SO3, notice that we have different central atoms, but we have the same number of oxygens. So in this case, chlorine, HClO3, chlorine is a little more electronegative than sulfur is, and thus HClO3 is the stronger acid than H2SO3. If you have two oxyacids that have both different central atoms and different number of oxygens, then it's difficult to make a comparison, and that's not a question that I would ask you to answer. I'm only going to ask you about oxyacids that either have the same central atom or have the same number of oxygens. Those are the comparisons we can make. All right, I have two slides here that have tables just summarizing the relative strengths of acid-base or a conjugate acid-base pairs. So we can see the stronger the acid is, the weaker the base is. So here, the strong acids have extremely weak, or basically bases that can't even really act as bases, and then the really weak acids are going to have stronger conjugate bases. Another slide here, again summarizing the acid and base strength with the conjugates shown across from one another. And this last slide summarizes strong acids and conjugate bases and how these are related to one another. To put this all together, the stronger an acid is, the weaker its conjugate base is. The stronger a base is, the weaker its conjugate acid. So we have basically an inverse relationship between the two. The strongest acids bases have essentially neutral conjugates because their acid and base are so strong, their conjugate can't really even act as an acid or a base, respectively. Strong acids and bases are extremely reactive with K values, equilibrium constant values, far greater than 1. Weak acids and bases are very stable with K values far less than 1. Whichever side of an equilibrium reaction has the most stable species, products or reactants, is always favored. This means that the side with the weaker or more stable conjugate acid base will predominate at equilibrium. So one last practice problem for you to try. Based on the chemical reaction shown here, classify C5H5N as either a strong acid, strong base, weak acid, or weak base. And then bonus question, which side will be favored at equilibrium? So please pause the video and try this question. All right, the answers here. We have water and C5H5N. If we look at what happens from the left to the right side, it looks like C5H5N is accepting an H+, so I would refer to C5H5N as a base. I see double arrows here, so I would call this a weak base, which makes water a weak acid. This would then be the conjugate acid, and it's going to be a weak acid, and this is our base. This is the conjugate base. OH minus hydroxide would actually be qualified as a strong base. So then bonus question, which side will be favored at equilibrium? I would say the left side will be favored at equilibrium. So referring back to this slide here, whichever side of an equilibrium reaction has the most stable species is always favored, meaning the side with the weaker pair will predominate at equilibrium. Here we have a weak base, weak acid, strong base. And so this side has the weaker combination. This side will be more stable and would thus be favored at equilibrium. All right, that's the end of this lecture. I hope you enjoyed and found this helpful. As always, please reach out to me if you have any questions. I'll see you in the next video, and I hope you have a great day.